what?
No, I have a microphone. So I should start talking now?
Well, I should give instructions first.
Okay.
So when Andy asked me to be the chair, he enticed me to be the chair by saying I should keep you and Chris on time. So I think I need to start with an apology to Andy. I'm sorry, I don't know if I can do that. Anyway, so George, you'll have 15 minutes plus 5. I'll give you a 3-minute warning. Do with that as you wish. And yeah.
Start?
Start.
Okay. Well, I really expected that my talk shouldn't last longer than the thing I'm talking about, which is the emission lines that occur during rising light in metal poor Arillary stars. So that's what I'm going to talk about. What I won't talk about much is the hydrogen and helium absorption lines and their strengths and their comings and goings with phase and the turbulent velocities and bulk motions that are derived therefrom. So, and I should note the thing at the bottom, these are all based on spectra taken with the DuPont and Shell in the years 2006 through 14. Now, the talk is only concerned, where's this pointer? What do I point with? This thing in the middle? This, oh, I see. I'm only concerned with this little interval of phase here. That's all the whole talk is about that. Between phases 9,0 and 9,5, and the 0 point is based by the velocity minimum defined by the radial velocities of metallic lines. Now, in some stars, I should mention that the helium absorption line phenomena are observable during a much more extended portion of the pulsation cycle, all the way out to that dashed curve you see well beyond maximum light. Okay. Now, the helium measurements are straightforward. It's a weaker line, and it wasn't known for a long time to recognize it was there. But unlike the Balmer lines, the helium emission is not overlain by infalling absorption. Whoops. Well, wait a minute. Get ahead of myself. This is the pointer. The hydrogen is so abundant that throughout the declining light and during the infall phases, the spectrum is overlain by this strong H alpha line formed by the infalling gas, and it's redshifted. And it's present in all the spectra, whereas in the case of helium, it isn't. The helium, you see, it just a glimmer appears at phase 0.909 in this star. Then it grows stronger and stronger and stronger and stronger. And there's no absorption components to distort it. So it's an ideal line to use in the study the history of the emission phenomena, the shock phenomena during rising light. And here I point out to you that not only helium-1, but helium-2, 4686, is visible at these same phases. Now let's see. And here, Chris Sneeden was kind enough to make an average spectrum of the 4686 region in 8 RRAB stars, metal poor. They're arranged in order of increasing metal abundance, Fe over H starting at -2.8 and going to -1.5. And you see this average spectrum shows beyond doubt that the 4686 is present. So there's doubly ionized helium in this spectrum of this star recombining at a time when you see a line of neutral magnesium with an ionization potential of 7 volts, and helium-2 has an ionization potential of 54 volts, and they're both present in the spectrum at the same time, which tells you that the Arillary star spectrum at this phase of rising light is a rather complicated thing. Next slide. So there's just a single picture to show you the problem, the absorption produced by infalling gas. There's a strictly empirical, simple way to measure that flux. You can just use the S-plot routine of IRAF and count fluxes or pixel counts in that region, and it's an unambiguous measurement. But you know that must be an incomplete proxy for the underlying emission, which is approximated by some model like this one, a Gaussian of some sort in this case. And for that, you have to choose an arbitrary center. So the result is completely model dependent. That choice that I made is the wavelength system in the reference frame of the metallic absorption spectrum at any given phase. So it's a velocity and wavelength system dependent on the atmosphere gas containing the metal lines that form the spectrum. Ooh, that's a mouthful. So that you get that result when you make a model. You can plot the model fluxes against the measured fluxes with a diagram, and you see that when the lines are strong, there's a ratio of about 2 to 1. The model fluxes in my model exceed the measured fluxes by about a factor of 2. And they're correlated, but there are some unresolved issues which have to do with the measurement, how you measure the emission flux when it's weak. Now, these are my measured fluxes. I'm just going to stick to measurements because that's what I knew how to do all my life, just make measurements. And so here are the measured fluxes for 7 stars, all strong emitters. And well, what you can see is they rise on a short time scale, typically 10 minutes or so. And then soon thereafter, they fade away. And so that's the data that you have to deal with. And at first sight, it seems to be a hopeless jumble. But you quickly realize by inspection that the variations of the individual stars are systematically shifted relative to one another. And you can combine the data by using phase shifts like I've shown here. You have to pick a reference phase that you're going to use for all the spectra. I picked 0.92. And then you perform the shifts. And in fact, it's not just those two, but you can see that they're all correlated with one another. They're all phase shifted. So when you do those phase shifts, with the phase shifts are indicated in that table, this table here, star by star, the shifts in phase units, 6,000ths of a cycle, minus 9,000ths, et cetera, et cetera. And as I indicate in the blue line here, these shifts are comparable to the uncertainties in the 0 points of phase of the radial velocity curves. So I'm not sure that they're real at all. They may be just consequences of the way I reduce the spectra. Okay, let's see here. Well, this is the conclusion, the principal conclusion of my talk, and I haven't exceeded my time yet. The stars, RRAB stars, metal poor with strong emission, appear to exhibit a universal phase variation of H alpha emission flux during rising light. They go up and they go down. They're not quite symmetrical, but to make this diagram, I had to scale the emissions at 5876 triplet line of helium to H alpha by the use of Caru's model atmospheres. So, because the fluxes, observed fluxes in different shell orders depend on all kinds of stuff. The transmissions of the various optical elements in the shell and the wavelength sensitivity of the detector and all that stuff. So in fact, there are different universal phase variations for all the emissions of hydrogen and helium. For example, the helium triplet phase variations is narrower than the H alpha emission profile. You can see plainly there. So, but there's one for 6678, the singlets, and then for the helium-2, I can just make it the profile smear narrower, but that doesn't. It's too weak a line to do anything with. So anyway, universal phase variations, and it's my opinion, not being a theoretician, that any successful shock model or series of models of what happens to an RLI star during rising light ought to be able to predict this shape. So I thought when I was doing this that I was making a contribution to the possible investigation of shock waves in RLI stars. Now, here's my one allusion to the absorption lines. What I discovered was that the emission and absorption outflows, they have to be in the wake of the shock, lie along continuous sequences of constant acceleration during rising light. And I show that for 6 stars that would fit in this montage. The change in velocities amounts to about 100 kilometers per second. They're all very similar, and they lead to an acceleration which exceeds the dynamical gravity. For the dynamical gravity, I just picked canonical values for the mass of an RLR star. I picked 0.65, and I think I picked a radius of 5 or 6. So it didn't make much difference because you take the square root. But anyway, you can see, and the interesting thing for me about all this is that the helium emission reappears near maximum light. And you can see, I've pointed with those arrows, the open symbols, as they indicated here, the open circles are emission measurements, and the blue ones are outflow negative velocity expansion velocities, and these are the infall velocities. And here, the emission lines reappear near maximum light. And this reappearance, so far as I am able to tell, is a ubiquitous feature of metal poor RLI stars. It's small, it's very small, but if you do a chi-square, there's 20 or 30 pixels in that emission peak, and the probability that they exceed by chance over the continuum level is very small. So, and the other thing I noticed was the violet absorption component is asymmetric in this diagram, and the end of it is very near the velocity of escape. And I don't know quite how to interpret that, except that, well, and here's an enlargement to illustrate the asymmetry. So the symmetry is real enough. Why it's asymmetric, we could argue about. And what I think is that Bob Stellingwerf, who's not here today, might have something to say about this, because he presented a 3D model of RLI repulsation at a symposium honoring Horace Smith just about 10 years ago. And what he has said essentially in this paper, insofar as I was able to understand it, was that there was an accumulation of energy deposited in the outer, way far out in the RLI atmosphere by a succession of pulsation cycles, shock waves moving out. And this heated this outer region, something like a corona, like a solar corona. It's the RLI star analog of a corona. And then a Parker wind, sort of like a wind, would flow out of the star. And he actually showed a diagram showing that there were velocities of escape and particles leaving his model. And so I wonder if that's this asymmetric violet profile is a suggestion of an empirical way to verify Stellingwerf's model. And that's it for me. I finished my talk on time.
George. All right, we have plenty of time for questions. So I will try to monitor Zoom. I'm not sure what I'm looking at here, but we'll start with people in the room. We'll start with questions in the room. Chris can help me figure that out. Mario.
So a trivial question, George. In the universal profile of the emission that you showed,
Yeah.
as a function of phase, was it the same offset every time for all the species?
I didn't.
Sorry, so you calculated the phase shifts you needed to bring all the hydrogen emission into a universal
Yes.
profile. Was it the same? Was it the same offsets for the other emission lines?
Oh. I estimated the offsets independently for helium 5876. It was strong enough. And yes, the offsets were very similar.
Okay.
Yeah, they were very similar, but I didn't use the hydrogen offsets for the helium. I did the
But they
helium
were similar.
separately.
They were pretty similar.
Yes, they were similar.
Okay, Tim.
Right, just a comment, George. I think we saw in this talk something we've seen for decades, which is when you take a set of observations and at first glance they look like a scatter diagram, the way you make sense of those is to separate the wheat from the chaff. And that requires insight. And in fact, I think I've always told my colleagues, especially the younger ones, this insight is not something you learn by yourself. You learn by observing those around you who already have it. And so that's one of the characteristics I could have predicted that would show up in a talk of yours. And I just think that that's something we're all very grateful for.
Thank you very much.
Some good insight there. Other questions in the room? Anything online?
Two chats.
Okay, no questions on here. George, was there anything unique about the stars you selected to observe here?
Yes, it's a bias sample out of, some 50 stars that I collected such survey data for. These were the ones that had the strongest H alpha emission during their rising light. So it's a bias sample, biased in favor of strong shocks. I think it's strong shocks because the shock strength as defined by Mach numbers and so forth. And H alpha emission strength are strongly correlated. So it's a biased sample, yes. And I would hesitate to demand that all the rest of the stars obey this thing, but at least all the strong all the hydrogen emission line stars do obey it.
Okay, thank you. All right. Thank you, George. Let's thank George again.